This is the first video in a new chapter on thermochemistry. This section is about enthalpy and heat, and the main points are about energy transfer, thermal energy, and heat capacity. So, in order to talk about thermochemistry, we need to talk about energy in general and all the different forms that energy can take. So, as you know from your earlier science classes, energy is what powers the world around us, from the sun, from fossil fuels, from the food you eat, and it comes in many different types, depending on the type of work it's being used to do. It could be in the form of chemical energy, like in a chemical reaction. It could be in electrical energy, like the electricity you use to power things, mechanical energy by turning a turbine, thermal chemistry, like the thermal energy from the sun. It could be solar energy or biochemical energy. There's many, many different types. But in this chapter, we don't just care about energy, we care about energy transfer, because that's the most interesting part. So energy is transferred between objects. And it can be transferred in one of several ways. It can be an orderly transfer or a disorderly transfer. So if it's an ordered transfer, we call this type of energy transfer work, and we use the symbol W. And so if we wanted to illustrate that, if we had two objects that came into contact with each other and work was going to be happening, the transfer of energy would be in an ordered kind of a way. All of the molecules in the first object would be moving in the same direction together, and that's what would move the second object as work. The other type of energy transfer is a disordered transfer, and this is called heat. And we use the variable Q because we'd already used the variable H for something else. So if two objects come into contact with each other and there's a transfer of energy via heat, this is going to be a disordered transfer. There's going to be molecules in the first object moving in a wide variety of directions very quickly and in random directions, just like a gas in the previous chapter. And that's going to cause molecules in the next object to start moving in a faster, more disorderly way as well. So these are two different ways of transferring energy. And we are going to care more about the second kind, the disordered kind, here at the beginning of the chapter, because this chapter is about thermochemistry, which is about heat. And heat is the transfer of energy in a disordered way, and it's a particular kind of energy called thermal energy, one of those items in our list up there. So there's a couple of different heat-related terms here. So thermal energy, that's the type of energy in the objects, and heat is the transfer of that energy. It's like heat flow. So if we had two objects, and the objects were not touching, let's say one of them had a really high concentration of thermal energy. So we'll color it really deeply red. And then the other object will have a lower concentration. Whenever you have two objects, one of them is always going to be higher than the other. So we'll color that one sort of more lightly. And then right now they're not in contact. There's a gap between them. So a little bit later, now let's say that I've brought them into contact with each other. So now they're touching. One of them has very high energy. One of them has a lower amount of energy. And energy is going to transfer between these two. Whenever two items are in contact and the amount of thermal energy in them is not the same, there's going to be a transfer of energy. And just like when we talked about diffusion in the last chapter, the transfer is going to happen in the same way. We always transfer energy or momentum from high concentration to low concentration. So the hotter the higher concentration energy object on the left is going to transfer that energy into the object on the right. And so after that transfer is complete, it has been going on for a little while, the thermal energy of the two objects is going to be on average the same. It'll be an equal concentration that's roughly in the middle of the two values before. So we always transfer from high concentration to low. And so there's one more of these words, these important thermochemistry words. There's thermal energy, there's heat, and then there's the word that we use in real life, temperature. And temperature, just like we talked about in the gas law chapter, is a macroscopic snapshot. It's the large people-sized measurement of the energy. So you can never measure the temperature of one particular molecule. All you can measure is the thermal energy of a particular molecule. You can measure the temperature of a large flask with millions of molecules in it. It's a snapshot from a wide angle lens. So if we wanted to label these different items in our picture, we could say that this one with the higher amount of energy, we could call that hot, and the one with the lower amount of thermal energy, we could call cold. So temperature is more useful on a larger scale, but these are the more scientific variables. All right. So now that we've talked about the transfer of heat, let's talk about how much heat you can transfer into a particular object, because not all objects can be heated in the same way. Exhibit A, some people run warm and some people run cold, and it takes more energy to warm up some of them. So depending on the material that something is made of, different materials have the capacity to absorb more heat than others. And we call this capacity the heat capacity. And we use the symbol C for capacity. Now, the units for heat capacity are joules per degree Celsius. And I know what you're saying, Rachel. I took an oath to always, always, always use Kelvin whenever I referred to temperature for all of science. And I have to tell you that it is just in this one chapter that we use degrees Celsius for convention instead of Kelvin. So don't get used to it. So the heat capacity is the amount of heat absorbed by an object when the object's temperature is increased by 1 degree. We'll say 1 degree Celsius. Technically 1 degree Celsius and 1 Kelvin are the same size, but since the units are in Celsius, we'll stick with that. So the heat capacity is specific to a particular object. So you could specify this particular piece of metal and this other piece of metal have different heat capacities because they are different objects. So as you could probably guess from the units, the formula for heat capacity is heat over a change in temperature. And it's not just temperature, remember, because it's not just about how much energy is in an object. We're talking about heat transfer. And transfer is between an initial condition and a final condition. So whenever you see a delta in front of a variable, that always means final minus initial for that variable. So let's do an example. Let's say we have an oven mitt, because I love to bake. And then we used to have like a smaller oven mitt, child size. Not that I would ever let a child help me bake, because why would you? But they do make them at the store. So which one of these items would have a larger heat capacity? Which is to say, which one would take more energy to increase the temperature by the same amount? Well, if I lit a fire underneath both of these objects, the smaller object would set on fire first because it's smaller. So that means that the larger oven mitt is going to have a larger heat capacity, and the smaller oven mitt would have a smaller heat capacity. Not that you should ever light your oven mitts on fire, but that's of course what we do when we leave them on the burner for too long. Okay, so it can be kind of confusing that the heat capacity for the same kind of an object is a different number depending on how big it is. So we'd like to make a number that's specific to the material that doesn't depend on how much mass there is. So there's another version of this variable, and it's called specific heat, or specific heat capacity is its full name. And so some textbooks use a lowercase c. I like to write CSP because my lowercase and my uppercase c's kind of look the same after a certain amount of time, and I like to be clear which one I'm talking about. And the variable here is going to have grams in it. It's going to have mass, so we divide out that mass so that we can have one number for a particular material. So this is like a mass-independent heat capacity. And this is the number we use most of the time. So the formula for the CSP, or sometimes just the CP for short, Q over mass times change in temperature. And you should know there's also a molar version of this if you use moles instead of grams in your formula. So if you used N, the moles of a substance, you would get the molar specific heat capacity. So be prepared to use that as well. Okay, let's do an example of two different materials and compare them. So let's say this first material is wood, and that has a heat capacity of 1.76 joules per gram degrees Celsius. And then we have another material that we can make floor out of, or ground, I guess, asphalt. And that has a heat capacity of 0.9. I actually have a friend who did research on asphalt. Not particularly stimulating, but makes a lot of money. So let's say I'm deciding what to make my porch or my driveway out of. And I'm thinking about how hot it gets in the summer and how I like to walk around in bare feet and don't want to burn myself. So which material would hurt my bare feet the most on a hot day? These are the kind of questions that thermochemists like to ask. And while this sounds like something that's a common sense answer, we can use science to answer this as well. We just have to interpret this question in terms of science. So, hurting my feet, that is a question about temperature, about how much the temperature of that material changes when it sits in the sun. And which material, that means we need to look at the specific heat, because the specific heat changes with the material. So we can use this formula we just put up here, but what I care about is temperature. I'm trying to solve for how much the temperature changes. So I'm going to rearrange the formula with temperature on the left. So if temperature is on the left, we're going to have Q over M times CSP. So I'm going to do a theoretical calculation for the two materials. So I need to make up some variables for my condition. So let's say they're sitting outside in the sun, because that's what you do when you build a deck. And let's say that they've been sitting out long enough that the sun has given them 50 joules of energy. And let's simplify by saying we have 1 gram of each material. So the amount of heat is the same, the size of the material is the same. Let's see how much the temperature changes. Okay, so if we had the wood, we have 50 joules of energy. We have 1 gram of material, and then the specific heat of wood is 1.76 joules per gram per degree Celsius. And then if we had asphalt sitting in the same sun, also absorbing 50 joules, also 1 gram, and the specific heat of asphalt is 0.9. Okay, and my units cancel, grams for grams, joules for joules, and we're left with degrees Celsius. And if we compute the numbers, we're going to get approximately 28 degrees here and 56 degrees here. And remember, this is not the actual temperature outside. This is the change in temperature. So for the temperature from whatever it was at nighttime plus 56 degrees. So the largest temperature change is for the asphalt. And if it increases by 56 degrees during the daytime, I definitely do not want to be walking on that material with my bare feet. So the way we can interpret specific heat is that the larger the specific heat, the more energy it takes to heat up that material. Because it's important to understand what these variables mean qualitatively and not just how to use the math formula to solve for things. You need to know how to use it in a sentence. So a material that has a higher specific heat, like that wood, that material needs to absorb more heat before its temperature will change. So you need to give more heat to the wood to get its temperature to change the same amount as the asphalt. And since we're living in Wisconsin, this is the reason that the temperature near a Great Lake is so temperate, is because water has a very, very high heat capacity, and it takes a lot of energy to change the temperature of that lake. And the temperature of the lake affects the temperature of the air around it, and that's why the temperature of areas like this tend to be more temperate in the summer, because of the high heat capacity of water. So the next video is going to be about calorimetry and how to use heat capacity to calculate specifically how much heat is transferred.